Good day to everyone. Welcome back to Physics Lecture Series at MGR Learn Smart. Myself, Dr.M.Sundareeswari, Professor, Department of Physics, Dr. MGR Educational and Research Institute, Maduravayal, Chennai. The topic of today's session is Superconductivity and Introduction. This slide outlines the topic of today's session, namely electrical resistance and electrical resistivity, normal conductors and superconductors, what is meant by transition temperature, how the graph of resistance versus temperature varies among these normal and superconductors, the first occurrence of superconductivity, the Nobel Prize winning discovery in the year 1911, role of refrigerants, high Pc superconductors, again a Nobel Prize winning discovery in the year 1986, an overview of major applications of superconductors where one can appreciate and realize how the superconducting phenomenon has played a role in pushing out the frontiers of today's technology with which our mankind is enjoying a very many safe and easy way of life in our Mother Earth. Dear students, here let us recall whatever we have learnt in our previous classes on metals, the normal conductors. The electrical resistance R is given by the formula rho into L by A, where L will be the length of the material which is in the form of a wire, and A will be area of cross section of the metallic wire. Rho, the proportionality constant, represents the electrical resistivity of the given material. The unit of electrical resistance and electrical resistivity will be ohm and ohm meter respectively. We know very well electric current will flow through the metallic wire due to potential difference that exists between the ends of the wire. However, there exists a fairly low resistance. Electric current is due to the movement of electrons, which is in a direction opposite to the current flowing through the metallic wire. For normal conductors, electrical resistance is found to decrease with the decrease in temperature. Hence, before the discovery of superconductors, it was thought that metals can have zero resistance at 0 Kelvin, but in actual practice, you see, this is not true. Superconductivity is the phenomenon of certain materials exhibiting zero electrical resistance and at the same time the expulsion of magnetic fields below a certain critical temperature or the characteristic temperature called as the transition temperature, represented by the symbol Tc. Hence, for some material, the resistivity vanishes at some low temperature. Resistivity vanishes means the resistivity is completely becoming zero, and therefore its reciprocal, the electrical conductivity, will become infinite. And that is why we are saying here they become superconducting, and such materials are called as superconductors. The temperature at which they become superconductive is called as a transition temperature. In the below table, I have given some examples of superconductors: mercury, lead, aluminium, zinc and niobium nitride, whose transition temperatures are respectively 4.27, 1.175, 0.85, and for niobium nitride it is little bit higher, 16. All the temperatures are given in Kelvin. So from this table, what do we infer is that the temperature what we have to maintain is very, very low, because we know our room temperature is after all 27 degrees centigrade to 30 degrees centigrade, whereas this is nearer to 0 Kelvin, which is minus 273 degree centigrade. So we can realize how cold we have to maintain the temperature if at all we want to make a superconducting material. Here BCS theory. Here let us discuss the graph between electrical resistance versus temperature. I have shown three graphs below. In all the three graphs, we have taken resistance on the y-axis and temperature on x-axis. The first graph is meant for the conductors. The second graph is meant for the superconductors. And in the third graph, we have given the both. Now let us go to the first graph. Consider the first graph where the resistance is getting decreased as we decrease the temperature. However, even at 0 Kelvin, there is some amount of resistance left out in the given metallic material. In the middle graph that is meant for superconducting material, you can see initially the electrical resistance decreases with the decrease in temperature. And suddenly at one particular temperature, which is nearer to 0 Kelvin, the electrical resistance drops to 0. This temperature at which there is transition from the normal state to the superconducting state is called as a transition temperature. In the third graph, the blue line shows the curve for non-superconductors or a simply normal conductors, which is metallic material, and the red curve will be for the superconductor. Now in metals we know electrons are responsible for the flow of current. And in superconductors, what do you think? Which is responsible for the infinite amount of current? Let us see the answer while discussing the BCS theory. Leiden and Kömmerling-Onnes are co-workers in doing the research on liquefaction of gases and study of electrical conductivity of materials at very low temperature. In 1908, Leiden was successfully liquefied the helium gas at 4.19 Kelvin. Later, in 1911, K. Onnes accidentally noticed that resistance of mercury was almost zero at the temperature of 4.19 Kelvin. From the graph, one can find at 4.19 Kelvin, the electrical resistance is dropped to 10 power 5 times of its initial resistance. Therefore, ability of certain ultra-cold substances to conduct electricity with zero electrical resistance may be called as superconductivity. Okay, and for this discovery, Dr. Kömmerling-Onnes, a Dutch physicist, has been awarded the Nobel Prize in Physics in the year 1930. And in the year 2011, several scientific events have been celebrated globally to mark the centenary year on discovery of superconductivity. Unfortunately, most materials must be in extremely ultra-cold temperatures in order to become superconductive. Hence, research is underway to develop compounds that become superconductive at high temperatures, say nearer to room temperature. Even today, the research is on to increase the TC to the nearer to the room temperature. There are very many uses and applications for these materials. In the below graph also, you can notice that the trend of TC in the x-axis is shifted to the right hand side. So we are nearing to the room temperature. And coming back to a small note on the refrigerants that are used here, the liquid helium and liquid nitrogen. Which you will prefer? Liquid helium has the boiling point of 4 Kelvin, whereas later the liquid nitrogen that has found to have the boiling point of 77 Kelvin. Although liquid helium has a boiling point of 4 Kelvin and can be used to make material superconducting, it costs about $5 per liter, whereas liquid nitrogen boils at 77 Kelvin but only cost about $0.3 per liter. Moreover, liquid nitrogen is also abundant in nature. Therefore, we will prefer liquid nitrogen than liquid helium. Not only that, with the liquid nitrogen, a major breakthrough has occurred in the discovery of superconductivity that leads to the high TC superconductors. Yes, in the year 1986, a breakthrough was announced by IBM researchers Johannes Georg Bednarz and Muller, a copper oxide ceramic superconductor which was found to have a TC of 35 Kelvin, and such high temperature has not yet been reported previously. And by early 1988, another ceramic, this of thallium, calcium, barium, copper oxide superconductor, has found to have a transition temperature of 125 Kelvin. And these two scientists, Bednarz from a German physicist and Muller, a Swiss physicist, they were being awarded the Nobel Prize in Physics in the year 1987. As of 2021, the superconductor with the highest transition temperature at ambient pressure is the cuprate of mercury, barium and calcium, whose TC is 133 Kelvin. These copper oxide ceramic superconductors are found to have perovskite structure. This is the structure of yttrium-barium copper oxide ceramic superconductors, often called as 1-3 superconductors, highly anisotropic and brittle. CuO2 layers that are shown in green color are responsible for superconductivity. High Tc superconductors are of type 2 superconductors. We'll see later what is meant by the type 2 superconductors. Now, what is special about this high Tc superconductors? Why such importance has been given is that the substance with a critical temperature above the boiling point of liquid nitrogen, together with a high critical magnetic field and critical current density, would greatly benefit to the technological applications. That is the reason we are strongly emphasizing about the high Tc superconductors. This slide gives some more examples of high Tc superconductors and also list the applications of high Tc superconductors in electronics, basic research, microwave technique, medical technique, power engineering and traffic engineering. Let us now consider the overview of major applications of superconductors. First is the Maglev trains. Levitation is a process by which an object is suspended by a force against gravity in a stable position without solid physical contact. Magnetic levitation, here a superconductor repels a magnetic field, so a magnet will float above a superconductor. This virtually eliminates the friction between the train and the track. So this particular levitation is applied in the Maglev trains in Japan. They have constructed such trains whose speed is say 500 to 700 kilometers per hour. You'll be surprised to note it, and I have given a YouTube link where you can visualize the demo experiment on levitation. The second application is a particle accelerator. The other name is Hadron Collider. They are used to make extremely powerful electromagnets to accelerate charged particles very fast to near the speed of light. This is the world's largest and powerful particle accelerator. It consists of a 27-kilometer ring of superconducting magnet with a number of accelerating structures to boost the energy of the particles along the way. This tunnel lies deep underground to protect it from cosmic rays that might interface with the research taking place. And it was first constructed by the European Organization for Nuclear Research. A decade ago, you would have noticed they proved the existence of subatomic particle called Higgs bosons, or they call it by the name God's particle. Okay, it is thought to be the fundamental building block of the universe, dating back to the Big Bang billions of years ago. India has also significant contribution to this CERN, and it has been located in Vigyan Samagam, Bangalore, Department of Science and Technology, on a particular country. The third one is the E-bombs or electromagnetic bomb. These are the devices that make use of strong superconductor-derived magnetic fields to create a fast, high-intensity electromagnetic pulse that can disable the enemy's electronic equipment. They release nearly 2 billion watts of energy at once. They were first used in the year 2003 when US forces attacked Iraq's broadcasting facility. They will act as a jammer. In recent time also, you would have noticed in Russia-Ukraine war, they have used one such E-bombs. The disabling the electronic equipment means not only the networking facility, no electronic equipment would be operated. The domestic electronic equipment will also be not operated. Okay. This slide shows how efficiently the electricity transportation could be done if we have a superconducting generator. Superconducting generator about half the size of a copper wire generator, but its efficiency is 99%. So you can see in the diagram below, 28 copper cables between 14 bipoles could be replaced by only 1 MgB2 superconducting cable. Here comes the major application of superconductors, SQUID. That immediately comes into your mind will be a seafood, but here we are going to talk about the superconducting quantum interference device. They are used to detect even the weakest magnetic field and they are used in mine detection equipment to help in the removal of landmines and in medical imaging of brain. Landmine is nothing but a blast that has been put or hidden and inside under a land, and whenever some vehicle cross it, it will blast. So this SQUID is used to detect and remove such landmines, and also they are used in the medical imaging of brain and heart pulses. Here the list is getting extended. You can see very many applications of superconductors here. We have almost come to the end of today's session. In my next subsequent sessions, we will learn about the properties of superconductors and the famous Bodin-Cooper and Schrieffer theory called as BCS theory of superconductors, which is considered to be a successful theory for explaining the conventional superconductors. Before I conclude, I would like to share technology development is amazing work, of course, that involves Internet of Things. But the base for this technology development is the new inventions in basic sciences. Without the basic science, no expert can develop the technology. Hence, students come, join, learn, and contribute to this great science. Thank you for listening. All the best.